In this lesson, we're going to be focusing on the hyperbola and how to graph the hyperbolic function. So first up, we got to describe what the function actually looks like as well as how to label it. So as before, on the left side of the screen, I have where we derive the hyperbolic shape from the two stacked cones. If you take a vertical slice, you will see what looks like to be kind of two parabolas. So the first thing to note is that this is not going to pass the vertical line test. You can't draw a vertical line and not hit it at two separate locations. So this cannot be written as a function like you would a parabola per se. So that means when we get to the equations, we're not going to be able to isolate the y value. You won't be able to write this as an equation of y equals something in terms of x. But first, let's again talk about what the function looks like. So the function can look like one of the following. Either it can look like the first type, where it is going in a left and right orientation, or it can look like type 2, where it's opening in an up and down orientation. Now, first thing is that for type 1, it'll have two vertexes, aka vertices, left and right of each other. For type 2, the vertices would be up and down from each other. So those are the vertices, the vertexes of each corresponding hyperbola. Now there is an axis that runs through the vertices, and we denote those axes with a dotted line. And the mathematical name of these axes is called the transverse axis. And then the last key feature that we're going to talk about, which should come to no surprise, are these special locations inside of the function, inside of the curvature, that are called the foci. Now that we've determined graphically, at least a little bit, what the ellipses look like, now let's actually start about talking about what the graphing form for it looks like and what it looks like algebraically. So the graphing form is actually going to be two different equations. The first equation, which will be representing of the first type, so for type I, it'll be of the form the quantity of x minus our h value, quantity squared, divided by a squared, minus quantity of y minus our k value, quantity squared, divided by the b value squared, and that is going to be equal to 1. Or, for type 2, we have pretty much the same thing, except it's going to be the quantity of y minus k quantity squared, divided by the b value square minus the quantity of x minus the h value, quantity squared, divided by a squared. And that's going to be equal to 1. So again, do note the specific colors that I'm referencing. H represents the number next to the x. It is how we're going to be translating left and right. K is the number next to the y. That's how we're going to be translating up and down. You can think about A as the stretch and compression factor horizontally, because it's the number underneath the x value. And B can kind of be thought of as the stretch and compression factor in the horizontal direction, because it's underneath the y value. The last thing to take note is the colors that I chose, because remember the transverse axis, which I have in green, it is determined by whichever term is first or positive. If the x value is first, meaning it opens in the x direction, then the transverse axis is going to be determined by the value underneath the x. But if we're dealing with a type 2 where the y term is positive, then the transverse axis is vertical and it'll be the b value. So let's do a little quick example. So here in my example, I have the quantity of x minus 1 quantity squared divided by 16 minus the quantity of y plus 5 quantity squared all divided by 4 equals 1. So first thing to note is that my x value, the term with the x in it, is first. So this is a type 1 style hyperbola, which means that it's going to be opening left and right. All right. So now that I know which direction it's going to be opening, let's find our starting location. So we're going to be shifted to the right 1 because of the number next to the x, and we're going to be shifted down 5 because of the number next to the y. That will find us the location right here. This is going to be somewhat of the center of this hyperbola. So how do we graph this? Well, first, since my a value, the number underneath the x, is 16, and I want to know what a squared is, I imagine this as being 4 squared. That's going to tell me how far I'm going to move in the x direction to find the vertices. So I'm going to move from the x on my graph right 1, 2, 3, 4. Now I'm going to move left 1, 2, 3, 4. Now these are going to be the locations of my vertices, the blue dots I have in my diagram up here. Now, that does not mean that we get to forget about this 4, because 4 is the square root of 2. We're also going to need to actually go up 2 and down 2. Now, the reason for that is we need to find the corners where the green dot and the purple dot would meet. Like if we were going to draw a box, I want to find the 4 corners that they would meet at. So they would meet here, 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 and here, because this is the last feature of the hyperbola, which is there's actually going to be 2 sets of asymptotes. And the asymptotes are going to be generated by connecting the diagonal black dots. So I would draw something like this, and then something like this. This is what's going to form the boundaries of the ellipse we're going to draw. The last thing, again, because the x part is the first part, it's the positive part, it is going to open in the x direction, and it will look something like this. And this would be a rough sketch of the ellipse, of the hyperbola that I have as an example. Now do note that I have not marked where the focal points are. I will be doing that and showing you that in a subsequent slide. So let's go over what the point of learning what a hyperbola is in the first place. First, let's start with the formal definition. If you were to Google, look up in a math textbook, what is the formal definition of a hyperbola, you'd get something like this. It is the set of all points in a plane, the difference of whose distances from two fixed points in the plane is constant. All right, so what does that mean? Well, if I have 2 points, like here and here, and I measure the distance, for example, here, this coordinate, the difference between this distance and this distance is going to be some number. Let's just imagine that number is 10. All right? So the difference between the distance from our first point, one of the focal points, and this curve, and that same point on the curve and our second focal point, let's just say that difference between those two numbers is 10. If I instead decide to find a different location on the graph, let's just say right here, then the distance or the difference in the distance from this location and here and this location and here, the difference in those distances would also be 10. So every single dot on this curve, if you marked the distance from any location between the focal points, the difference is always going to be 10. Now, because we're saying the difference between the 2 points, it doesn't just generate this curve, it also generates this curve because the difference between the distance from this location and this focus and the distance from that location and this focus, that difference would also be 10. That is the definition of what a hyperbola actually is. It's all the coordinates whose difference between the location of that coordinate and the two focal points, that difference is the same. Now, what about the practical applications? Where the heck are you going to see this thing? Well, you can see this in a lot of different spaces, but do keep in mind this is the most complex conic section, so the applications are a little beyond what, say, you could do in high school. But one of the things it allows you to do, which I think is kind of cool, is it allows you to generate gears to translate rotational energy in a non like right angle kind of orientation. Because most of the time you have gears and cogs, if they're just, little traditional cogs and circles, you can translate it in lateral directions, up, down, but it's really hard to change it in an oblique direction, to change a rotational force in a direction that isn't just straight up and down or straight left and right. Another thing is if you create a sonic boom from an aircraft, the boom will actually hit the ground in the shape of not a parabola but a hyperbola. Next, if you have stacks for dissipating steam from, say, a power plant of some sort, the shape of the buildings is actually a hyperbolic shape. It maintains the structural stability while also minimizing the actual need for materials. And then finally, if you have an object moving through space that's affected upon by a large gravitational body, like, say, the sun, the trajectory it takes is not parabolic, it is actually hyperbolic. It takes on the shape of a hyperbola. So if you ever want to do anything in aerospace, this is going to take on a good bit of what you're going to be studying. All right, so I've got my two equations. Now we need to derive a formula for finding the focal length. Well, one of the nice things, if you might have noticed from that GIF we saw earlier, is that we're generating a lot of triangles, and triangles remind us of the Pythagorean theorem. And in fact, the formula to find the focal length, or C value, is actually going to be the A value squared plus the B value squared is going to be equal to the focal length C squared. Again, where C represents the distance from the center of the hyperbola to the focal length. So as like a little quick diagram, if I had something like this, here's the center, the focal points, that distance from the focal point to the center, that distance is C. And again, this also works if the transverse axis is vertical as well. So let's start with our first problem. Problem number one, I have the quantity of x minus 3 quantity squared divided by 25 minus the quantity of y plus 6 quantity squared, all divided by 9 is equal to 1. And I want to graph this thing. So let's start this off. I'm going to graph it by going right 3 and down 6. 1, 2, 3 to the right, down 6. That's going to take me right there. Now, in the horizontal direction, I'm divided by 25, so that tells me the square root of that is 5. So from my center, I'm going to go right 1, 2, 3, 4, 5. Left 1, 2, 3, 4, 5. The number underneath the y term is going to be a 9. Square root of that is 3, so I'm going to go up 1, 2, 3. I'm going to go down 1, 2, 3. And then I can form my box to determine my asymptotes. Again, I'm looking for a sketch, not exactly what it's going to look like. I know it's going to open left and right because the x term is first, it's positive. So I know it's going to open in the left and right orientation. So it's going to look something like this. But the last thing I need to know is like, okay, where do I put my x's for my focal points? Where are those two locations? So I'm going to do the Pythagorean theorem. My a value squared, which is 25, plus my b value squared, which is 9, is going to equal c squared. 25 plus 9 is going to be 34. So 34 is going to be equal to c squared. We're going to square root both sides to get rid of the second power. Don't forget your plus or minus. And we're going to get c is equal to plus or minus the square root of 34. We're going to be graphing, so let's get decimals. Let's not try and simplify this radical because we're actually trying to apply this number to something. And it's going to be approximately equal to, so not exactly, approximately equal to 5.8. 3. All right, so there's my C value. That's the distance from our center to the focal point. So I'm going to go right 1, 2, 3, 4, 5.83, which is roughly around right here. Then I'm going to go left 5.83, which is roughly around right here. And those are my focal points for problem number 1. Now, for problem number 2, we kind of got a little bit of an issue because problem number 2 is not written in the graphing form that we are used to. So we're actually going to have to do some math before we can do any of that. So again, note that my forms require that this equation be equal to 1. Right now we're equal to 32. So I'm actually going to take the entire equation and divide everything by 32 because that's my biggest problem is I need this to be equal to 1. Once we accomplish that fact, we're going to get 2y squared over 32. 2 divided by 32 simplifies into 1 over 16. And then 8 over 32 would turn into 1 over 4. So this is going to be x squared divided by 4 equals 1. And now we're in a format that we like. Now there's no adding or subtracting happening with the x or the y. So that means we're not moving left or right. That means our center is going to be right at the origin. The value underneath the y squared is 16. Square root of that is 4. So we're going to go up 4. We're going to go down 4. The number underneath the x to the second power, I don't know why I put it to the fourth, is going to be a 4. Square root of 4 is 2. So we're going to go right 2 and we're going to go left 2. Find our 4 corners so that we can generate our asymptote. Or asymptotes, I should say. Now, if you want to generate more accurate asymptotes, technically what you should do is you should determine the slope between the opposite corners, and that will generate you more dots because it's just a linear function. But I'm just good with a quick little sketch for right now. Now, in this one, my y value is first. So that tells me it's going to be a type 2 hyperbola. It's going to be one that opens in a y-centric direction. So I'm going to quickly sketch something that looks like this. There, there. Lastly is I need to find my focal length, my C value. So it's going to be my A value squared plus my B value squared. So it's going to be 16 plus 4 is equal to C squared. That means 20 is equal to C squared. I would square root both sides. Don't forget your plus or minus. And I would get that C is going to be approximately equal to, if you want to simplify it, it's 2 root 5, but I want a decimal answer because I need to put this on a graph. It's going to be plus or minus 4.47, so about 4.5. So from my center, I'm going to go up 4.5, and I'm going to go down 4.5, and those will be the locations of my focal points. The very last variation that I want to go over is one where we actually don't get an equation. We want to find the equation, but we're given certain pieces of information. So problem number 3, I've got a center at -1, 2. I've got a vertex at -1 comma 3. Notice they only give me one of the vertices. I don't have the second one. And they actually tell me the focus is at -1 comma 2 minus root 5. So they're nice enough to just give me the non-decimal version, which is actually very, very, very helpful. But let's backwards map this. So first, center is at -1 comma 2. So we're going to go left 1 and then we're going to go up 2. So there's our center right there. So at the very least, I know it's going to be x plus 1 in the parentheses, and I know it's going to be y minus 2. And I know that because that's how I would get that center. They say the first vertex is going to be at -1 comma 3, 1, 2, 3, which is right here. And with that occurring, then we automatically know that if that's the vertice, that it's going to open upwards and downwards. And if the distance from the vertex and the center is 1 up, then there should also be another vertex 1 down. All right, so we found our center. We've used that piece of information. Check. We found our vertice, and then from that found the other vertice. So we use the second information. Check. But now we typically need to know, like, how far to the left and right do we go for these minor vertices that don't really show up on the graph. And this is where a lot of students tend to get stuck. They tend to not understand how might we derive the minor vertices. And you have to look at the third piece of information that a problem will often give you. It'll give you the focal length. Notice it says that we are going to be having a single focus, so there's going to be multiple, at left 1 and then up 2, but then we're going to subtract root 5. So we're going to go up 2, and then we're going to subtract or go down root 5, which is like, it's around right around here. But the way that we get the focal length is from the formula a squared plus b squared equals c squared. A squared plus b squared equals c squared. But we now know the focal length. The focal length is going to be 2 minus the square root of 5. So my c value is going to be the square root of 5. Because again, that's my distance, 2 minus the square root of 5. So if I go down the square root of 5, that's my focal length, root 5. And then I already know my A value. My A value is the distance from the center to the vertex, which is 1. So this is going to be 1 squared. But what we don't know is the B value. I now have a formula, 1 squared plus B squared equals the square root of 5 squared. I can calculate my B value. This is going to turn into 1 plus B squared is going to equal 5. Then I'm going to subtract 1 to the other side. Get B squared is equal to 4, which is really useful in and of itself. This is going to be useful for when we write our equation. But we want to actually find the B value, so we're going to square root both sides. Don't forget the plus or minus. And we're going to get B is equal to plus or minus 2. So that's going to be how we find the minor vertices. We're going to go from our center, left 2 and right 2. That will allow us to draw the 4 dots. Because remember, we are still also trying to graph this. Have our asymptotes. I know from the problem it said that our vertex was at -1 comma 3, which is this vertice right here. And that also means that we're also going to get this vertice. So I know it's going to open in the upward direction. Looking something like this. I know that my focal point is going to be left 1, and then my y value is going to be 2 minus root 5, which is approximately -0.24, which is like right around here. So that means the next one's going to be right around here. And now my graph is complete, but now we should, again, finish our backwards mapping and write the equation. I know the y value is going to be first. The y term is going to be first because it opens up and down. So it's going to be the quantity of y, and we've gone up 2 for our center. So we're going to go minus 2 quantity squared over the distance from our center to our vertex is going to be 1. So that's our a value. So a value squared, 1 squared is 1. Minus the quantity of x, and we've gone left 1 to get to our center. So that means I need a plus 1 quantity squared divided by, well, now our minor vertices, the vertices that we don't use for hyperbolas, I've moved 1, 2. So that's my b value. But the number that goes underneath is going to be the b value squared. 2 squared is 4. That's equal to 1. So here is our equation generated from knowing the center, the vertex, and the focus.